Okay, hi everyone, let's move to the indexing section. This section is also one of the most important sections for database systems. I hope you can spend some time on this section to going over these materials very carefully, as well as the textbooks. So this section can provide us with different data structures we can use to maintain the index tables inside your database system, which can be used to help us to do the queries in a much more efficient way. And before we go to this section, I have a toy question prepared for you, which is also correlated with this section closely. So we have a question like this. Let's assume, given a list, the list L equals to what? Equals to, inside the list we have different numbers like 1, 3, 7, 8, 12, 10, 14, 25, 13, and etc. We have a list, and the question is to search for a number like 17. Check if the number is in the list L or not. If yes, return its index, or otherwise just return true, return false. I hope you can follow me for this question. Given a list, we want to search for a number. A specific number, we provide you with the example of 17, and we want to check if the number is in the list or not. If the number is in the list, provide the index. Index means which position this number is. We have 1 number, the index is 0, 3 number, the index is 1, index 2, index 3, and etc. And we're starting the index from 0. If it is in the list, return its index, otherwise just return false, denoting this number is not in the list. So if we have this question, then how can we do this searching? I can give you some time, you can think about it, and you should have different strategy to do the search on your paper. Okay, I hope you have the answer on your paper already. So normally if we have a question like this, this question is a very common question. If you do the interview with different components, they will have some question like this, right? You need to provide different answers and solutions. So this question is correlated with data structure, right? The course we learned before, as well as the algorithm course. So when we have question like this, we need to provide the answer. A very straightforward answer we can have in our mind is to we just go over all the numbers inside this list, right? We can check one by one to see if this number is a good match with a desired number or not. So the first solution we can have in our mind is very simple. It is linear search, right? I hope you know what I mean, right? So for the linear search, we can go over all the numbers in list L and match with the desired. If the number matches, we return the index. If we cannot find any matching numbers within the whole list, in other words, we're going over all the numbers of the list and we cannot find a matching, then we can return false, right? So this is a straightforward solution we have in our mind to do the linear search. Then the question will be, what is the time cost for the linear search? If we denote the length of the L to be n, then the linear search the time cost will be about the bigger O, right? n. I hope you know what is a big O, right? It's a time complexity notation, right? We know from the algorithm course. Besides the linear search, do we have any other better solutions which have not much lower time cost? Another scenario we have in our mind maybe probably is to, because right now we didn't mention if the list is sorted or not. If this list is sorted, then we can do the search in a much faster way, right? We just do the binary search, right? If this list is not sorted, so far we find this list is not sorted, right? We have this number 12 before 10. And so probably another way we can do a search is to step 1, sort the list, right? I think you should know some sorting algorithm, right? The time cost will be big O n log n, right? The faster algorithm we can use to do sorting probably is n log n. And then step 2, if we have this need to be sorted, then we can use binary search to find. Its time cost will be what? It will be log n, right? Okay, so this is another potential scenario we can have. We can do the sorting first, and then we can do the search. Compared with the linear search, it seems this time cost together is much more than big O n, right? Because here we have n log n. It's larger than this big O n. However, let's assume if we have so many different searches, in other words, we have to search different numbers for so many times, then the time cost for this kind of search will be big O n times the number of desired searches here, right? However, here if we have this sorting, if we have different searches, we just need to sort this list once, right? In other words, this time cost for sorting actually is acceptable if we have so many different searches. If so, then this second solution will be a better solution than the first one, right? Because time cost on search will be much fewer than the first one. We just need to sort the list once, and we can do different binary search for different numbers for so many times. So therefore, the second one will be a better solution. In this section for the indexing, we will do the searching actually. So given a table, we want to find some tuples matching our desired attributes in our condition, right? We want to search, which is very similar to this question we show here. We need to design different data structures to help us speed up the searching process. So for the database system we introduce in this section, we use both a linear search as well as the second one, similar to the binary search to help us. And for maintaining this sorted list, we have another data structure to help us, which is like a tree structure. With tree structure, we can both sort the list as well as do the binary search. Okay, so this is a question. I hope you can follow me for this question, right? It can provide us with some high-level ideas about the materials to be introduced in the indexing section. Okay, let's move back to the slides.